Okay, we're now going to talk about real exponents. In general, all real exponents. So this one's probably going to be in two pieces. We'll talk about just numbers, and then we'll kind of talk about the more decimal approximations and decimal values. So one of the main objectives of pre-calculus math is making sense of real exponential functions, such as 2 to the power of x or 10 to the power of x, where x is a real number. And some features of exponential functions that you would tell your students. So I'll let you consider those. There are obviously a ton of them, and maybe you tell them how they're interrelated with quadratics, or with, not quadratics, with radicals. Maybe you tell them how they're interrelated with radicals, because radicals are really rational exponents. Or maybe you tell them how they're related to logarithms. However you define these, however you want to define them, maybe you talk about how they grow exponentially. That's fine too. But consider how you would tell them. Consider multiple ways to tell them, because interestingly enough, when I tell you guys something one way, it doesn't always click, and it won't click with your students one way. Some ways I have to explain things differently, just like you guys will have to do that. So please, practice that. So let alpha be a positive real number, not equal to 1, because 1 is really boring. And R and S are rational numbers. Then alpha to the R is positive. If alpha is greater than 1, then alpha to the power of R is also greater than 1 for any R greater than 1. If alpha is greater than 1 and R is less than S, then alpha to the R is less than alpha to the S. Now again, I'm saying the alpha is greater than 1. We showed that's not the case between 0 and 1. So the graph of alpha of R will have one of the following two basic shapes, depending on whether alpha is greater than 1 or alpha is between 0 and 1. So greater than 1, we expect it to be rising, right, at an exponential growth. Less than 1, so alpha is a value less than 1. It's a small fraction, so we expect it to get smaller, getting closer and closer to 0 the farther we go up, the more that we raise it to. Raising a fraction that is less than between 0 and 1 up is going to make it smaller and smaller. So recall that a sequence of real numbers is an arithmetic sequence, right? You guys remember the definition of arithmetic sequences, right? Arithmetic sequence, if the difference between consecutive terms is constant, it is a value, it is not changing. A sequence of non-zero real numbers is a geometric sequence if the ratio of consecutive terms is constant. So what I want you to do is prove that if x to the x sub I is an arithmetic sequence, then alpha to the x sub I is a geometric sequence. And here alpha is any positive real number, right? So I'm saying alpha is a positive real number. And this one I typed in here because I didn't feel like it was that bad. But yeah, so proof, I'm going to let xi be an arithmetic sequence. Then by definition of arithmetic sequence, from any xn plus 1 minus xn, it's equal to k, and k is a constant. Right, I know k is a constant. This is the property. This is the difference between consecutive terms is constant. That's what this says. Okay? Now I'm going to let alpha to the power of xi be a sequence for alpha in the real numbers. Taking a ratio of any two consecutive terms, so this is this, right? These are all, this is alpha, and these are all in a power, right? That's all a power. Okay, from the properties of exponents, right? That's the properties of exponents. We've already shown that. This exponent minus this exponent. But we've already shown that this is the same as this, and it's equal to k. So we have alpha to the power of k, and any positive real number raised to a constant is also a constant. Hence, the ratio of any two successive terms of a sequence is a constant. And by definition, geometric sequence, if the ratio of consecutive terms is constant, which we just showed, it's a constant, alpha to this is also a constant. So by the definition of the geometric sequences, a to the xi is a geometric sequence. Period. Right? Or put a box, because this was a proof, right? I proved it. And then it says, what does part 6 say? Part 6 says alpha, f of x is alpha to some x for some unknown alpha. Suppose that the value of the function is known for one value of x. Okay, so we're going to say f of c is equal to lambda. So we want to show that this information completely defines our function, and we can solve for alpha in terms of c and lambda. Okay, so the uninteresting part, right? The uninteresting part. If, let's see. So we have this, let f of x for some alpha. And maybe just because of room in this, from here, right? And let f of c equal lambda when x equals c, but does not equal 0, because not even interesting, right? That's not even fair, right? Okay, so then what does that tell me? Well, x is c, so when alpha to the power of c, it's going to equal lambda. So alpha to the power of c is going to equal lambda. And maybe I'm going to go ahead and take the log of each of these, ln of alpha to the power of c is equal to ln of lambda. Okay. Now, why do I use ln and not log? Well, it's one less letter to write. And I'm a mathematician, and we like to be lazy. I can pull the c down, so I have c ln of alpha is equal to ln of lambda. Okay, well, Maybe I want to divide by this c first, right? Let's divide by the c. Divide by the c. So I have ln of alpha is equal to ln of lambda divided by c. Now, because I used ln, well, I mean, this would have worked if I used log. I just would have had to raise it. Put a base of 10. I'm going to raise each of these to the e. I'm going to give them a base of e. So then I have e to the ln of lambda is equal to e to the ln, ln of, not lambda, e to the ln of alpha is equal to e to the ln of lambda over c. Well, e and ln filter each other off, so I have alpha is equal to e to the ln of lambda over c. What are some properties I could do? Let's clean this up. Let's see. This is okay, I see it now. So alpha is equal to ln, e to the 1 over c ln of lambda. But just like before, I can take this and put it up there. So now alpha is equal to e to the ln of lambda to the power of 1 over c, right? That's pretty valid, okay. But now the e to the ln filters off. So lambda is equal, or alpha is equal to lambda to the power of 1 over c. Now, that has solved alpha in terms of c and lambda, but is it really? So let's see. I am told that when x is equal, so this becomes, right, that f of x would equal alpha to the power of x. But I know what alpha equals. It equals lambda, maybe to the 1 over c to the power of x. And this is going to equal lambda to the x over c. And I'm told that when f of c, it's going to equal, let's see, it's supposed to equal lambda, right? That's what I'm told right here. It's supposed to equal lambda. I even built it to equal lambda. So let's plug a c in instead of an x. So this becomes lambda to the c over c. Well, c over c is 1, which is going to just equal lambda. So this does check out. Thus, f is completely determined. Bam. What else do we got? What else do we got? What's next? Let alpha be greater than 1. One of the most important features of the exponential function. Features of the exponential function alpha to the x is that it increases much more rapidly than any polynomial function as x approaches infinity. We illustrate this property with the exponential function 2 to the power of x and the polynomial function x to the power of 5. Create a table of values for x to the 5th, 2x, and 2x minus x to the 5th for integers, 1 through 40. You can do this with a spreadsheet. You can use Mathematica with the following command. If you want to learn how to do Mathematica, it does give you that command. So create a table of values. You could use Excel to do this, but you are creating a table of values for 40 different values in 40 different inputs for 3 different functions or functional relationships. So this could be way more than you think to do unless you use something like Excel. And then it says, look at the chart, right? So I want you to look at the chart. Which value, x to the 5th or 2 to the power of x, is greater when x equals 40? Well, figure out which one's more, right? That's pretty straightforward. And you should know what to expect here. I'm not going to do that. From the spreadsheet, it is clear that the graph as x goes to x to the 5th and x as x goes to 2 to the x cross at least 2 places between 1 and 40. Use graphing technology to generate clear graphs of these crossing points. I would use Desmos. That's what I would do. And I would limit your x values at a couple of locations. For the first picture where it crosses the first time, because if you show the whole thing, you're not even going to be able to see one of them. I would limit the graph to be between 1 and 2, because it's going to cross there, okay? And then the next one, I would limit it up to 30 so you can see the next cross. D, one might try to argue that 2x is eventually greater than x to the 5th by graphing the two functions. 2 to the power of x is eventually greater than x to the power of 5 by graphing the two functions on the same axis and comparing the graphs. Try graphing both of them on the same axis for 1 through 40 and look and see if it provides better information than the spreadsheet. The spreadsheet, there's an interesting property. When you do the g minus the 2 to the power of x minus x to the power of 5, when f is less than g, you should get a value that is greater than 1. When g is less than f, you should get a value that's in the negative. And you're going to see it go from negative. Does it start negative? Oh, I don't remember if it starts negative or not. But wherever it starts, you're going to see it flip signs, and then you'll see it flip signs again farther up in the spreadsheet. When you're talking about it graphing, you'll put it up there. You'll set it between 1 and 40 and see if the graph provides better or worse information than the spreadsheet. And then suppose the student looked at the spreadsheet results and the graphs and was not convinced that 2 to the power of x remains larger than x to the 5th for x greater than 40. What's to keep them from crossing one more time, the student asks. What mathematically convincing argument could you give to prove that 2 to the power of x is greater than x to the power of 5 when x is greater than 40? And I want you to consider that. This one, you're going to use Excel or spreadsheets. You're going to take pictures. If you want to do this all by hand, that is your choice, but please understand that you're going to need to write these all out. You will not approximate values. And to be honest, I can tell you that when you check it at 40, G, let me write here, G minus F is equal to so I would not choose to do this by hand, right? You shouldn't. You should use software. Mathematica is a good choice if you're familiar with Mathematica. If you're not familiar, most of you are familiar with Excel and Desmos, so they're useful tools for this. And I think that was it. All right. All right. Have a good day.